the next step.
So Radiant's working on a 1 megawatt portable nuclear microreactor that can be mass produced. And the reason it's 1 megawatt is if we made it much larger, you could not easily ship it around on a truck, and you could certainly never put it in a big transport aircraft. So the size of the thing we're working on, we can do both of those things. And what we want to do is make 50 reactors per year so that we get really, really efficient at doing it. And having it be fully portable means you can actually do mass production the first time ever, gives you the highest reliability, the lowest possible cost of construction, right? Just from learning by doing, getting a high rate of production. And when you have a portable nuclear reactor that's this size, we can send it to literally anywhere in the world. And then also very cool, it can just come right back. So the customer, they can have clean nuclear power, last for years, and not have any nuclear fuel on their site. It stays in the system and we just bring it back and handle it for them.
I'm Isaiah Taylor. I'm the founder and CEO of Valor Atomics. Valor Atomics is making thousands of nuclear reactors for heavy industrial power. So data centers, metals electrolysis, and making abundant clean hydrogen. And we'll actually use that hydrogen bonded with CO2, and we can actually make all of the hydrocarbon fuels that currently power the world. I've been thinking about this company for a long time, basically since I was 12 or 13. I grew up thinking about nuclear energy around the breakfast table. My great-grandfather was a nuclear physicist on the Manhattan Project. I knew my great-grandmother for a long time, and we used to just sit down, over breakfast and talk about the Manhattan Project and Oak Ridge and the story of nuclear energy. So I spent a long time thinking about it, and I wanted to know, why did nuclear not scale to be the major power source for the world? And I spent a few years trying to answer that question. I think it's a technology question, it's a politics question. And, I think I formatted the company in a way that solves all of the critical problems with it, and it's going to allow us to actually scale for the first time.
I'm Julie DeWall. I'm the co-founder of Antares. At Antares, we're building microreactors, small ones that can go after critical infrastructure for largely military use cases, but also commercial off-grid use cases.
I'm Jordan Bramble, CEO and founder here at Antares. I previously worked in the White House at the Office of Management and Budget, and I have a lifelong passion for physics and complex systems. Well, the single biggest thing I learned is how the federal budget process works and how large government acquisition programs are led. And it turns out in nuclear, you kind of need that too to get reactors built. You need to be sufficiently technical, you need to understand how Washington works, and you also need to understand how to capitalize a business. So really what makes us different is our approach to this problem. We actually like to call it strategic energy. And what that means to us is using the unique characteristics of nuclear fission to enable things that would otherwise be impossible with other forms of energy. Example of this that maybe we're all the most familiar with is the naval nuclear programs have actually built something like 4.5 times the number of reactors as the entire commercial sector. We don't do that because the energy's cheap. We do it because it allows us to put submarines underwater with nuclear weapons on them anywhere in the world for 6 months at a time, undetected. And if you really zoom out and take a broad view, let's look 10 years into the future, we could be using that same propulsion technology to power underwater autonomous systems, and they could go underwater undetected even longer. Our belief is that a heat pipe cooled system allows us to do both underwater, terrestrial, and space-based use cases.
You have, let's say, remote ground stations, remote missile defense sites, like those need to be 100% working, and they require energy. We know that today our missile defense sites up in Alaska and the Arctic are working off of diesel generators. Not enough, right? You don't want to have something where the fossil fuel supply chain could cause, your systems to be down. These are really important, and I think, deterrence and having your systems at the ready, people know that there are no holes to poke in it. That's exactly what the military is looking for.
My name is Brett Kugelmass. I'm the founder and CEO of Last Energy, and we develop micronuclear power plants for the heavy energy intensive industries such as factories and data centers. We deliver on-site to our customers to serve in a plug-and-play manner. So we offer electricity as a service, but at our core, we're designing a nuclear product. And I say product pretty intentionally, because one of the other challenges that we've seen historically with the nuclear energy industry is costs just go up, 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 while in every other industry, the more you build something, costs go down, down, down. And so the key was switching from this construction project to manufactured product mindset. SMR stands for Small Modular Reactor. It's a class of nuclear power plants that aren't as big as the traditional ones, hence the S in small, Modular means they're trying to use more modernized construction techniques. And when we think about modular, we want to take it all the way to the limit. How can everything be built in a factory and virtually nothing done on site? To us, that's the epitome of what modular means.
When I went to leave SpaceX, it was because the DoD announced a thing called the Pele program.
We are currently in the process of beginning to build the reactor. It is a prototype. It's going to be built in Virginia, and it's going to be tested in Idaho. And the prototype is never going to leave Idaho. But the Department of Defense has to decide if it wants to build more nuclear reactors in the future.
They asked specifically for 1 megawatt or more portable reactors that are under 100 tons. And that's really what set the stage for thinking about this, because I think that the DoD is an entity that can be the first customer, can help fund development, and can help put some positive, constructive pressure on the regulatory structure so that we can build again and deploy these things. So a lot of aspects of the design are frozen by like, what does that one major customer want? And then we went from that point to figuring out that actually there's a bunch of interesting commercial customers. There are these like remote villages and like remote mining operations that in Canada and Alaska and other places that could be supported. And so then we went, well, what if we pool all of those customers and mass produce? That's the basic framework for how we got to what we're focused on now.
Well, we're working right now on our demonstration unit, which is our first reactor unit minus the nuclear parts, so minus the nuclear fuel and things. That just says, hey, can we put all these pieces together? Can we get our systems to work? Can we get our materials to function at the temperatures we want to work at? And that first milestone should be hit in the next couple of months. We're really excited about that. And I think that just proves ourselves as a team, right? Being able to work together, build with a cross-discipline team, something that is net new. Granted, all of the materials we work with have been used before, but this sort of combination of it is a new thing. And so we're really excited about this demonstration unit.
Now, there's also a safety principle embedded in this as well. When uranium atoms split, the neutrons that leave are actually traveling too fast to cause more fission when they first leave. And you actually need to slow them down. And the way that you slow them down is called a nuclear moderator. So a moderator is a material that essentially bounces these neutrons around until they're slow enough to contact another uranium atom and cause more fission. And what's interesting is that there's this safety principle baked into nuclear physics. And that is that as moderators heat up, they actually become less effective as moderators. And what that means is that the neutrons stay in fast spectrum and eventually get absorbed into other materials rather than causing more fission, which means that the rate of nuclear fission reduces in the core. And eventually, the core should be hot enough that your nuclear reaction actually stops altogether. And that's a completely passively safe reaction. Now, the only way to take advantage of this principle is to choose a nuclear moderating material that has a very high melting point, because you want that effect to take place where it gets so hot that the reaction just shuts down well before the melting point of the core. And our reactor is exactly like that. We use graphite as our moderator. Graphite has an extremely high melting point, and long before we would get into a meltdown state, the nuclear reaction would just cease altogether.
I want to say it's true that every reactor design is fail-safe. Typically, reactors have control rods, which if you cut power by gravity, they fall into the reactor, and it shuts the reaction down. And there's a huge number of them, so they don't even all need to function for that to be true. If you put control rods in our reactor, you have a risk that if there's a high rate of heating of the gas that's inside, that pressurized gas can throw the control rods out. And that has happened in earlier reactor development history. But so what we use instead are these control blades that go in a circle, in a cylindrical fashion around the core. And those control blades can rotate into or away from the reactor and control the reaction in that way. And so they can't be ejected from the system. And then in our design, if you heat up the fuel and the graphite in the system, it will also naturally reduce the reactivity and shut itself down, like render the reactor subcritical.